Hello, hello, hello. So, today I'm going to discuss with you the solutions to our latest coupled oscillator problem. Two springs, one attached to the other, and they are hanging vertically, so they're in the gravitational field. The top spring has a spring constant K1, and below that is mass M1, and below M1 is another spring constant K2, and at that end is a mass M2. And the question now is, what are the two normal mode frequencies of that system? I would urge you to look at the solutions of my problem 43, because they are effectively identical. The whole method is identical. There's one little pinch that I gave it, that instead of having the two springs horizontally on a frictionless surface, I had them hanging vertically in the gravitational field. So you ready? I'm ready. If you have one spring constant K and mass M at the end, hanging vertically, and this is the position at which M is not moving, it's completely standing still. So it's the equilibrium position. So there is a force mg down, and then of course, since there is no net force on the object, the spring force must be mg upwards. So now if I lower this object over a distance x, according to Hooke's law, the restoring force from the spring will be minus kx. And so gravity has nothing to do with that anymore. Moving this over a distance x, the restoring force will be kx in that direction. Therefore, if you write down the differential equation, ma equals minus kx, you will find that the resonance frequency of a single spring hanging vertically, assuming that you can ignore the mass of the spring, that omega is the square root of k over m, the standard result that we have seen countless times. In other words, this frequency is identical to putting the spring horizontally on a frictionless surface and letting it oscillate in this direction. Again, omega is then the square root of k over m. So once you recognize that, you might as well change our problem to putting the two springs in series on a horizontal frictionless surface. So that you can never get confused by mg forces, which have no effect on the final answer anyhow. So this would be a better way for your algebra. If you did solve it vertically, of course you would still find the same result, but your math would be a little bit more confusing because you have mg values in there. I have no mg values if I have them here. So, m1 is at rest here and m2 is at rest here on a frictionless horizontal surface. I displace m1 in this direction over a distance x1, and I displace m2 in this direction over a distance x2. It's now very easy to calculate the net forces on 1 and on 2. The net force on m2, the restoring force, only depends on the length of this spring. And if this spring is now longer by an amount x2 minus x1, the restoring force must be K2 times x2 minus x1. With the minus sign, of course, but in opposite direction. This equation is sign sensitive. In other words, if x2 were smaller than x1, this equation would still be correct. Where is it? This equation would still be correct. Because the restoring force would then not be in this direction, but it would be in that direction. So don't think that it is important that I choose x2 to be larger than x1. I choose that because then it's obvious that the new length is larger by an amount larger than it originally was by an amount x2 minus x1, and that determines the restoring force. You see that here. On M1, this same force that is in this direction on M2 must be in that direction, because the spring is connected here and there. So that is the x2, k2 times x2 minus x1. You see that? It's the same, except now it is in plus direction, so you see the plus. But the net force on M1 is also determined by the length of this spring. And this spring is no longer by an amount x1, so there is a force in this direction, kx1, and that's a minus sign. So look at these two equations. They are at the heart of our solution. So the restoring force on x1 is given both by the length of this spring and that spring. The restoring force on x2 is only determined by the length of that spring. Once you have this, you have effectively tackled the problem. The rest is just a little bit boring algebra, which I work out in problem 43 in great detail. Since a normal frequency means that the frequencies for both objects have to be the same, I substitute for x1 c1 times cosine omega t. And I substitute for x2 c2 times cosine omega t. These omegas must be the same. Of course, c1 in general is not c2. I substitute x1, this x1, in here. And I substitute x2 in here. So this x1 goes in here, and the x2 goes in here, and x2 goes in here, and x1 goes in here. So now I get one equation here, which of course has an omega square in it, and this equation will also then have an omega square in it. So this equation now, with these values substituted in it, I can calculate what now C1 over C2 is from this equation. But independently, I can calculate from this equation what C1 over C2 is. It's a function of omega squared because of the second derivative. And the C1, C2 here is also a function of omega squared. So, I take the value from C1 over C2 that I find from this equation with these substitutions, and I take the value of C1 over C2 from this equation after substitution of these equations, and I put them equal to each other. That's what you see there. So here you see C1 over C2 of one of those two equations, and here you see C1 over C2 due to the other equation. Well, you can write this in a simple way. Remember from your high school days, ax squared plus bx plus c is 0. I repeat it, ax squared plus bx plus c is 0. The solution is that there are two solutions for x in general. X is minus b plus or minus the square root of b squared minus 4ac and the whole thing divided by 2a. That's what I do here. So you have to massage this algebraic here a little bit, that it gets the form omega squared. No, it gets into a form that the equation is ax squared plus bx plus c is 0. And the x in that equation, ax squared plus bx plus c is 0, the x in that equation here is omega squared. So it's really high school algebra. So you'll find here that x is minus b divided by 2a plus or minus the square root of b squared minus 4ac divided by 2a. b is negative, so minus b is positive, but when you take the square of minus b, that is the same as the square of b squared. So this is a little boring. That is not. That's where the physics is. And this is just a matter of massaging to find omega squared in the way you would have done in high school. Ax squared plus bx plus c is 0. X is minus b plus or minus the square root of b squared minus 4ac, the whole thing divided by 2a. When I found this result, I sort of asked myself the question, are you sure that it is right? It's not so obvious when you look at it that it is right. So, in a way, maybe I cheated. I don't consider it a cheat. I substituted in this equation m1 equals m2 is m, and k1 equals k2 is k. So this then becomes 3mk, and this one becomes 3mk. So it's then very easy to calculate the two values for omega. And I did that. And then I went to the web and I asked the web, what are the normal modes in a system like this if K1 is K2 and M1 is M2? And they gave me the exact same answer that I had. So I was pretty convinced that I had not made an algebraic slip. So this had to be correct because of my consistency check, and so now it becomes trivial to finish it because we know the values for M1, M2, K1 and K2. So you find here omega squared, so you can calculate what omega is. The plus value here is of course when there is a plus here, and the minus frequency is of course when there is a minus here. So I substitute these values in here, and I find for omega plus 0.684 radians per second. That makes f plus the frequency in hertz, the highest frequency 0.109 hertz. That's the period, a little more than 9 seconds. And I find omega minus this value with a frequency in hertz of 0.0287, which is a very long period, 34.8 seconds. How realistic, of course, this experiment could be done, I do not know. That was not really what I had in mind. Yes, it would be 30, almost 35 seconds, and that's the way the numbers came out, and I had no intention of changing my numbers so that they may look more like something you could do at home. You cannot do this experiment very easily at home. If the period is 34 seconds or more, there may even be other issues that come in there. But in any case, there are no other issues in my problem. So these are the answers. Now that I record the solutions, I haven't seen yet any of yours. I haven't even posted this problem. I only gave this problem to see whether you have learned how to solve normal frequencies of a simple coupled oscillator. Two springs in series, you can't have it simpler. Problem 43 was much harder because that was an object attached to a spring and a pendulum attached to that object. That was much harder. The method that I followed is identical. Okay? Take care. Have a nice day. And I assume you still want to be friends. And I hope that I get at least 50, maybe 70 solutions. I doubt whether the fraction, the percentage of correct values will be 70%, even if it were 40 or 50%. I would be delighted if I get 50 to 100 answers. All right? Okay, I would like to add something. And that is, now that we know omegas for the high frequency and for the low frequency mode, we can also calculate now, of course, the ratio C1 over C2. You can choose any value for C1 you want to, which is the amplitude of object number 1. Then in the resonance mode, in the normal mode, then the amplitude of the second one is determined. Because C1 over C2 is then one unique value. Remember, this was C1 over C2, and this was C1 over C2. So I'll just pick this one. If I picked this one, I would have found the same result. I know what K2 is, I know what K1 and K2 is, I know what M1 is. If I take omega in the plus mode, and the plus mode means the highest frequency, and I substitute that omega in here, I have to square it, then I find that C2 is minus 1.79 times C1. The minus sign is an absolute must. If you hadn't found this to be minus, you've made a mistake. Because the whole idea of the high frequency mode is that they oscillate like this. Same frequency, but they are 180 degrees out of phase. It's not obvious that in this case C2 is 1.8 times larger than C1. So now you take omega minus and you substitute that in here. Then you'll find that C2 is plus 1.11 C1. You better find the plus, because that's the mode, the lowest frequency mode, in which they both go like this. They go in the same direction at all moments in time, so they're in phase. The amplitudes are different, of course, but they come to a halt at the same moment in time. So yes, it is a must that you find here a plus and here a minus. It's sort of interesting that in this case, in the low frequency mode, C2 is only 10% larger than C1. Not so obvious. In the high frequency mode, C2 is almost twice as large as C1. Okay, so I thought that this would give you a little bit more insight. Keep in mind, you can not solve for C1 and C2, because it depends on which amplitude you give the system, and you're free to do that. So you can choose C1 or you can choose C2, but you cannot choose both, because the ratio is fixed by the resonance frequencies. Alright, I hope this was useful, this edition.